Hello everyone. In this video I am going to explain the parallel adder and how we are going to model or how we can implement this parallel adder in multisim, as well as how we can have the VHDL code, structural modeling of the VHDL code for the parallel adder. Okay, so let's start with this parallel adder. Already we have discussed in my previous video about the full adder. Simply a full adder, also a full adder using half adder. Now, as you can understand, the problem of the full adder is that if you are going to say add more than a single bit, that is, say for example 4 bit, so what you need to do is every time you say for the first time, first column you have to apply with the C input or the carry input as 0, and you have to take the copy the output sum and carry, and the carry goes to the next column, and the second time again you have to apply A1 B1 along with the carry that being generated in the previous state. Again you need to record the sum one, and so on and so forth. So what we need is, if we can have a device where we can apply all the 4 bits simultaneously, okay, and also we should get the result simultaneously. So in that case we need to have a parallel adder. So parallel adder is nothing but a combination of or cascading of full adders. Okay, suppose we are going to make a 4-bit parallel adder. So this 4-bit parallel adder consists of 4 full adders in parallel: full adder A, full adder B, full adder C, and D. So in which the first full adder you are applying the least significant bit of both the numbers A naught B naught, then in B A1 B1, and C A2 B2, and in full adder D A3 B3. So in the full adder A, it also requires a carry in signal. So obviously in the first column of addition, 4-bit addition, first column here the carry is 0. So what you need to do is you need to apply 0 all the time here, and you will get the sum naught here and carry naught C naught here. Now as in the second column, in the second full adder, we are applying the second column, that is A1 B1, and that carry is being propagated from the full adder A, that is the first full adder. So the carry out of the first full adder will go as a carry into the second full adder. Similarly, carry out of the second full adder will go as a carry into the third full adder, and so on and so forth. Now at this point you can ask one question, that since in the first full adder, in case of the first column, since the carry is 0, carry in is 0, so instead of having a full adder we can have a half adder, because in half adder there are 2 inputs, there is no carry in. So the first full adder can be replaced by an half adder. Yes, that is true. So it will minimize the cost as well as the hardware requirement, because full adder at least it requires 1 3 input XOR gate. As you can see in this circuit, 3 input XOR gates, or 2 input XOR gates, and 3 AND gates, and 1 3 input OR gates. But in half adder there requires only 1 2 input XOR gate and 1 2 input AND gate. So that way it will minimize the cost as well, the hardware requirement as well as the cost, also the propagation delay and all. But thing is that if you think for the modular, that is true, you can replace it with a half adder. But thing is that if you think of modular design, modular design means, suppose now you are making a 4-bit full adder, 4-bit parallel adder. Now suppose tomorrow I want a 16-bit parallel adder. So in case where suppose I need a 16-bit parallel adder and I am having a 4-bit parallel adder already with me, then I can cascade 4-bit parallel adder to make a 16-bit parallel adder. So in that case, this first full adder, the first adder has to be a full adder. Otherwise, if it is a half adder, then you cannot consider it the complete 4-bit parallel adder as a module for a 16-bit parallel adder. Hope you understood. So in that case, that means for modular design, we always prefer to have the first one also a full adder instead of a half adder. But if you explicitly design only a 4-bit full adder, 4-bit parallel adder, then it can be a half adder as well. The first one can be a half adder as well. Okay. Now let's start making this in Multisim. So this is your Multisim workbench. So in this we need to import the different components required. So here we need full adder. As you can see, we need a full adder. So we will not going to design a full adder separately here, because in this Multisim the full adder block is available. I am also not going to use the full adder IC. There is full adder IC available, that is your TTL IC 7482. So this 7482, this is this 7482, this is a 4-bit, a single bit full adder, but it is a dual full adder. That means inside this IC 7482, which is a TTL IC, in which there are full adders. One is this A1, A2, with A1, B1, and C0, then with A2, B2, also with C0, and outputs are SUM1, SUM2, and this C2 is the carry for both. Okay. So but without this also there is instead of this also there is another direct full adder block. You can type full adder. Okay. So full adder, there is full adder. There is a full adder. The master database only it was there. Let's see. Yes, this one, full adder. In all families you will get this full adder. So you can use this full adder. Actually this is made up of that AND gate, OR gate, AND gate, OR gate, XOR gate and OR gate. Okay. So you see here A input, B input, C in input, SUM and carry output. So this is a full adder. You can see by double clicking on it. These are the user fields. You see there is no vendor status, price and all, because it's a module, not an IC. And the pins different. A is input, C in also input, B input, carry output, SUM output. This status means you are including all. You can exclude if you don't require. So you can exclude, but I need it include to be included. So there is no values because it's a module. Display you can sense, label also you can sense. So let it be full adder A. Okay. Oh, sorry. It should not be, there should not be any space. So it's a full adder array. This is already there. Okay. Now let me rotate it 90 degree because I want the input side in the upper side. Inputs are in the upper side, outputs are in the lower side. So I need this full adder of 4 times. So I am just copy and paste it. Okay. Suppose this is a full adder. full header A. This is your full header say B, and then this is your full header say C, then this is your full header say D. Okay, so once got it. So from the carry out of the first full header, as you can see here, the carry out of the first full header goes as a carry in for the second full header. So this is the carry out of the first full header, so it will go as a carry in to the second full header. Okay, let this level should be in the, okay, let it be here, no problem. Now the carry out of the second full header will go as the carry in of the third full header. Then carry in out of the third full header goes as an input to the carry in to the fourth full header. Okay, now it's all, connection is done. Then you need to apply the inputs here. So I need some source. So for that source, so digital source, so digital interactive design constraints. So I need this. Okay, let me rotate it. Okay, so this is my so this is, I just change the level. This is my A naught, suppose. Okay, then let me keep all this below. Okay, so this is my A naught, and so this is my B naught. Okay, now suppose this is my A1, and then this is my, sorry, this is my sorry, this is my okay, this is my A1 B1. Similarly, this is my A2 and this is B2, say. Okay, A2 B2, and then this is your A3, then this is your B3. Okay. Okay, so all the inputs are get connected, then you need to connect the indicator. So indicator also again I'll use this probe only, so let it be blue probe. So I'm going to rotate it. Okay, let me make it at least 3 volt or 3.5 volt, then it will be better. Okay, so this is for S0, let it be S0 level S0, let it be S2, S1, then S2, then S3, and one more for C3. Okay, so that's all. A0, A, B0, A1, B1, A2, B2. Okay, so let's save it. I'm saving it in my app drive, DBCT Multisim DSD, so it is ParallelAdder. Okay, now let us test with this as per these examples. So 1 1 1 0 1 in A, So 1 1 0 1 in A. Okay, 1 1 0 1 in B. 1 0 1 1 1 0 1 1. Okay, so let's run it. So you see, as per the results, 0 0 0, S0 0, S1 0, S2 0, S3 1, C3 1. So this is S0 0, S1 0, S2 0, S3 0, C3, S3 1, C3 1. So that means it is working fine. Okay, let us see it another example. So instead of this, if I make it 0 and then it will be 1, 0 plus 1 1, 1 plus 0 1, then 1 plus 0 1, then 1 plus 1 0. Okay, so only difference is in A it is 0 1 0 1. So as you see, S0 1, S1 1, S2 1, S3 0 and C3 1. Okay, so that means perfectly all right. So this is your 4-bit parallel adder using 4 full adders. Then next, the same thing I am going to do it in VHDL. So in VHDL, I am opening these Xilinx. So in Xilinx, as already you know, to start with, in Xilinx, go to the file menu, new project. So in the new project wizard, you need to give the project title, project name, by which a folder will be created in the designated location. This is the location. Okay, my location is correct. So I am putting it as a ParallelAdder PSA. So this is a command description. This is a 4-bit parallel adder. So top level source of VHDL. Then next. So again, as in my previous video, I mentioned this wizard is for setting up the hardware in which the logic is going to be tested. But here we are not going to connect any hardware, only we are going to simulate. So there is nothing to do with this wizard. So simply put next. This is the summary and finish. Okay. So here you now next is go to this is the actually product category. As I mentioned, the hardware we are not going to use, so by default it is taking whatever it was. So right click on it, then click on the new source. So in the new source, you are going to add the VHDL source. So you have to click on this VHDL module and give a file name. Now again I am telling you, this file name should be different from the project name, number one. Number two, this same file name is the name of the file that is going to be created with .vhd extension, that is the source file VHDL file. Also the same file name will be the name of the entity of your program. So let us put it as parallel adder. Okay, so I click on this VHDL module, ParallelAdder, add to the project, location should be the same. Okay, my file project is PA. Okay, so next is you are going to give the ports. that is the input output. Now as you know, as you can see here, this parallel adder, it's A is a parallel bits, B is a parallel bit, so it has to be in a form of bus, and in coding it is called vector. So A is a vector of length 4, B is a vector of length 4. So how you can give? There are two ways. If you are directly putting it in this port only, then you need to click bus. But in case of coding, if you write it, then it should be vector 0 to 3 or vector 3 down to 0. So let us put it here, like say A input, and it is a bus. While it is bus, you have to give the ms bit and ls bit. So ms bit is my 3, ls bit is say 0. Similarly, my B is also a vector, which is also in the bus, so it's a 3 and 0. Then sum is all my output S, sum S0, S1, S2, S3. So it is output, it is also a bus, so it will be 3 to 0. Then we need one extra C in, okay, so C in for this. These are intermediate. I am going to design the parallel adder using full adder as a structural component in VHDL. So this VHDL program will be a structural program. So we need not to define this C0, C1, C2, but we have to define this C3 as an input here. So this C in as an input here. So C in as an input, so it is a single input. Now this C3 is also an external output, so you have to put C3. These are the variables, whatever you would like to put. So C3 is also output, but it is a single output. So that's all. These are the ports. Next, so you can see the summary that you have assigned, the different ports that you have assigned. So finished. Now you can see the program here. Okay, this is the design summary. Actually, you can see the entire summary here. Okay, this is the ParallelAdder program. As I mentioned, the file name is also this ParallelAdder.vhd, as well as your entity name is also ParallelAdder. So in my previous lecture, as already I mentioned, these green things are comments. Comments are being made by 2 hyphens, and the first part of the program is the library declaration, and this comes automatically, and so it's a default library IEEE.stdlogic1164.all means it will include all the component of this library. Second part is the entity declaration. As I have defined the ports, with that ports it declares the entity automatically. Okay, so entity ParallelAdder, as I mentioned, you see in the while you have assigned those ports in the port entity wizard, there you have given A as a bus and ms bit 3 and ls bit 0. So as I mentioned there, that while you write it in the program, it has to be vector. So you see A, which is in std vector 3 down to 0. It can be also 0 to 3, same thing. Similarly, B is also vector input, but vector 3 down to 0. S is output, but as a vector 3 down to 0. C in is a single input, C3 is a single output. Then in ParallelAdder, which is the entity name. Then architecture, the name was the behavioral, or this is just the name. Okay, so architecture is the keyword. Anything blue is the keyword or the command or the instruction. So architecture, behavioral is the name of the architecture, off is the keyword, then ParallelAdder is the entity is. Now the main part of the program will begin here. Now since it is going to a structural program with which is a 4-bit ParallelAdder with full adder as a structural component, so we have to make that structural component here. So again, go to this ParallelAdder, right click on it, new source, again click on the VHDL module, click give some name, say let it be full header. Okay, so it has to be the same file, add to the project, yes. Now let us finish the full header part. Say A is my input, already we did the full header in my previous lecture. So ABC input, say sum and carry are my sum and carry are my outputs. Okay, finished. So this is your full header program. So let us first finish the full header program. Okay, this full header can be your structural program or can be a behavioral program. So let me finish it as a behavioral. So full header, this begin, after this begin, as we know, we have to start one process. So process, what to process? The inputs A, B and C. So process begins here. Then the sum output is assigned with A XOR B XOR C. Okay, similarly the carry is assigned with A and B or B and C or A and B and C. Okay, then end the process, okay. So that's all in behavioral, that's all for the full header program. So full header part is done. Okay, full header part is done. I am just copying this part. Okay, so full header part is done. So let's save it. Okay, so this full header part is done. Then go back to the parallel header part. Okay, so before, since it is a structural program, before the architecture begin, you have to declare the component. So for declaring component, the keyword is component. So component has to be declared as it was declared in the entity of the component. So that is why I have copied component full header is, then end component, exactly same as that of the this part. Okay, so then after declaring the component, here we are going to now declare some signals. What are the signals? The C dot, C1 and C2, because these are the intermediate things. Okay, so C0, C1, C2. So it has to be defined as a signal, because this is the output here and input here, output here and input here. You can define it as an in-out as well. Okay, so before this beginning of this, I need to define the signal. So for defining signals, the keyword is signal. Say C0, comma, say C1, C2. So these are also STD logic. Okay, signal C1, C2, C0, C1, C2. These are the signal being defined. So signals are defined. Next, the processes begin. Here you need not to declare the process statement. Directly you can map. So for mapping, you have to give some label. Say according to this, full header A, full header B, full header C, I will give some names. So let us consider it as full header underscore A. Then say full header B, full header say C, and full header say D. Okay, colon. So what is the component? Component is the full header. So you have to write this component as it is, full header. Then port map, port map within bracket. So you have to do it for all of this. So I am just copy and pasting. Okay. So in the first full header, what you need to map? As you see, in the first full header, A naught, B naught, C in, and S naught, C naught are the output. So my A naught, B naught, C in are external inputs. C naught is my internal, that is defined as a signal. S naught is my external output. So how we have to define? First, A naught. So as A is defined as a vector, as a bus, so you cannot write simply A0. It has to be write like this: A within bracket 0, that is A naught, comma, similarly B naught, B naught. Then C in is my external input, so it is like C in. Then sum out, which is also a vector. S is a vector here, so therefore S naught within bracket, S naught, and C naught is my output, which was a signal. So here it is C naught is defined individually, so you need not to write it in a bracket as it is. So C naught. Okay. Next is in the second full header, your A1, B1, and instead of C1, that C dot, the C naught as a C in here, so it is C naught. Then output is sum 1 S1 and the signal C1. Okay. And the third one, it is your A2, B2, then C1, S2 and C2, and your fourth one, it is your A3, B3, then your C2, S2, and it is your C3, which is your external carry output. Okay, semicolon for terminating the statements, then in behavior. That's all. It's done. So just save it. Okay, once you save, you see these are the components comes under this ParallelAdder. Okay, so the programming part is done. Next, you need to check the syntax. So for checking syntax, as you see here, this should be there in the top level source of the ParallelAdder. Means this indication of the top level source should be in the ParallelAdder, because my top level source is the ParallelAdder. So just click on it, then under the synthesize access T, you can see the check syntax. So it is checking the syntax for the my ParallelAdder. Check syntax is going on. Check syntax is going on. For the first time, it while you run it for first time, it takes a little more time. You can see the result here. So it is completed successfully. That means there is no syntax error. Similarly, you can check this full header as well. Check syntax for the full header program. that is this program. So section text made it correctly. So next is the simulation. So click on this simulation. Now go to this, right click on it and new source. So now we are going to add test bench, say ParallelAdder underscore say tbw. This is the name, file name. So this VHDL test bench. There is no VHDL waveform here. I mean test bench waveform here. So we have to go for the VHDL test bench. Add to the project. Next, as you see there are ParallelAdder full adder, so it has to be for the ParallelAdder. Next, finish. So it will create one again .vhd program, that means a VHDL code for the test bench. So this is the program. Component is AB, all this is there, signal A, B, C in. Again, here I am not going to use this clock because it is a combinational logic. So no need to have this clock. You can make it comment here, no problem. Then since we are not using this clock, so this part also not required. Okay. Now for A naught, A1, A2, B naught, A naught, A1, A2, A3, B naught, B1, B2, B3, you have to make this process. Okay. Also for C in. Since C in is 0, so you can make C in always equal to 0. Initially it is initialized with 0, so you can make it for 0 forever because it is anyway 0. Okay, so here also this clock is not required. Wait for 100 nanosecond. Let it be 50 nanosecond. So for 50 nanosecond it will be 0. After that, so let it be steam process 1. Then A naught, because it is a vector. It is a vector, so A naught is assigned to it. Not A naught, that means it becomes 1 now. Then say let it be wait for say 100 nanosecond. So the same process will be for A1. So it is same process 2. Now I make it say 100. Just arbitrary timing I am giving. So it is 1, A1, A1. Now I am making it 100. So now I am making it say 150. Okay. Similarly, for this is A1, so this similarly for A2, this will be steam process 2, steam process 1, 2, this is 3. Okay, so now so let it be 150 nanosecond. This will be your A2, so wait for say 200 nanosecond. Then similarly steam process 4 for A3. Now it is supposed to 200. Let it be 200. Now A2 here, and here I have given 200, so I will make it 250. Just 250 nanosecond difference I am making. Sorry, 50 nanosecond difference I am making. Okay. So then for B, so steam process 4 5. Now this is again so I am starting here with suppose 200 nanosecond. Now it will be your B, this is your B, and wait for another 200. I am starting at 200. Okay, then this I am copy and paste here. So now it is 6. So now I'll make it 250. Then it is B1 and B1. Here also I'm making it 250. Then 6 7. So like I'm making it 300. This is suppose B2. This will be your B2. This is your B2. Then this will be say 300. So let it be 350 just to make reference. Then 8. So it will be your B3. This is also your B3. I'm making it as 400 say. And this suppose 350. Then the last is for C in. So it will be your 9 here, because it is already 0, so I can make 1000 nanosecond wait. So it is your C in is with 0 only, and wait for another 1000 nanosecond. That's all. So now this test bench will check whether there is any syntax error or not. So I am checking the syntax for this test bench code. Okay, so completed successfully. Then I am going to simulate it. So this is the TBW. So simulate behavioral modeling. So it is simulating in a separate window. It will open up. Okay. So this is your test bench. You can see here, this is your A, this is your B, and the C in is always 0, and this is your sum output. So let us see, something is wrong while, because it is A2 is considering don't care, somewhere A2 is considering don't care, right? So let's see what was the problem. A2, again I am checking A2, this is your A2, right? This is don't care. Something is wrong with your A2. So this is steam process 1, A0, 2, A1. A0 and A1 is okay, no? A0 is okay, A1 is okay, A2. And in the A2, A3 is also 0. Okay. A1, steam process 3, A2. there is no problem. Something is wrong in A0 not A0. 59 is 102. Okay, this 100 again I am making it. Not A1, wait for stream process 3. 150 nanosecond. A2 not A2, wait for 200 nanosecond. Stream process, oh, these two are A2, yes, that is the problem. So here it is A2, this is also A2, this should be A3, right? This is the problem. Okay, so let us close this, and sorry, let us close this. Oh, then run it again. Okay, so okay, now if you look at this somewhere, suppose here, your A is 1110. Here I am putting A is your 1110. This is your 1110. B is your 0011. B is your 0011. So result will be 1110, 110, 1101. So 1001. Now let's see this first one, U3, that is sum 3, is showing undefined. So let me say in the main program there is something wrong in the main program. You see, this also I made it S2, that is the mistake. So S1, S2, this should be S3, no? That is the mistake I did. Okay, so let me close this and run it again. Okay, now see, this is your A, this is your B, this is your sum. Anywhere you just check, suppose, okay, let me check this 1110 0011, 1110 0011. So result will be 10001. So 0001. You see, this 0001, and this is C3 only. So C3 is, where is the C3 here? C3 is also your output, C. This is C3. So C3 is 1 here at this point. Yes, this is 1. So that means it is correct. Okay. So likewise you can check anywhere else. So if all 1 1 1 1, let's see. If it is 1 1 1 1 and B is your B is your 1 1 1 1. So it will be like here only I will see 1 1 1 0 1. So result will be 0 1 1 1 0 1 1 1 and carry will be 1. Yes, correct. Okay. So let's stop this. Then let us see the implementation again, in which for this see the schematic. So start with the schematic. Okay. So this is the complete adder, parallel adder. Okay. This is the internal these things, parallel adder. Okay. Again I am just looking at technological schematic. This is the technological schematic of the entire these things. These are the inputs and different inputs in the bus form, since it is given as a bus form, and this is the sum out as a bus form. This is the C3 output, this is A in a bus form, B in a bus form, and this is C. Okay. It is showing A, B, B, C, A, C, and A XOR B XOR C. The internal full adder part. Okay, so that's all. In my next video I will show how the same parallel adder can be make for subtractor as well. That means adder comes subtractor. I will explain in my next video. So thank you for listening. Hope you understood. If you have any query related to this, please contact me.